Hello everyone. This is another video from the design interview preparation series from Code Karle. So in this video, let's look at how do we design Twitter. So now let's look at some of the functional and non-functional requirements that we want this platform to support. Okay, so from the functional side, the very first thing is we should be able to tweet, which is basically saying that we should be able to post a content of 140 characters length. It could have image, it could have a video content, it could probably have links to external websites and all of that. Okay. The second requirement is something called retweet. So if somebody has tweeted something, you should be able to retweet that, which is very similar to a share on Facebook. Okay. The next thing is you should be able to follow someone. Now that is a directed relationship. So if let's say I follow user A, does not mean user A also follows me. Okay. So that's a unidirectional thing. The next thing is you should be able to search for some particular content within all the tweets that have been posted on Twitter by some users. This would be usually used to do some trend analysis or to figure out what's happening in the world, or in case if you want to just read about what people are talking about a particular topic. So, for example, if Game of Thrones has launched and you want to see what people are saying about it, you can probably search for it. Okay. So these are the functional requirements. From the non-functional side, one of the very good to know or important to know things is it is a very read-heavy platform. So if let's say one user is posting something that is seen by a lot of users, right? So for each write that is happening into a system, there are a lot of reads that is happening. Statistically speaking, I don't know how much correct this number is, but I've read it somewhere that Twitter has 100 times more read traffic compared to the write traffic. Okay, so that is one of the very first NFRs that the system should be able to support that kind of access patterns. Now, these are the list of NFRs that we'll be looking at. The next thing is it should be able to render very fast. So if somebody wants to look at their home screen or basically timeline kind of a thing, that should render in less than a second. Okay, the reason being to basically improve the user experience. Now, when you are tweeting something, again, that flow should be fast. So you should get a success response saying that your tweet has been posted successfully. So basically, both of these two translates into that the system should be having a very low latency, and at the same time, it should be always available. Okay, this system cannot go down. But in some cases, lag is okay. So when we say lag, it does not mean that the page will take seconds to load. What it means is that if somebody has posted a tweet, I might be able to see it after 20 seconds. So that is okay if I'm seeing a content later. But whenever I'm seeing it, it is rendering very fast. So that's how we want the site to load. Okay. Now let's look at some scale numbers. Okay. These are probably real Twitter numbers, but I'm not sure how correct they are. I just read it somewhere, so I'm quoting that. So Twitter has roughly 150 million daily active users. What this means is 150 million users access Twitter daily on the read path at least. Some of these could be writing as well, but most of them would be reading. Okay, and Twitter has roughly 350 million monthly active users. Again, 350 unique users access Twitter on a monthly basis. Okay. Overall, Twitter has roughly 1.5 billion user accounts. These could be accounts of people or organizations or anybody, right? It would probably also include a lot of fake accounts. From a tweet scale perspective, Twitter has roughly 500 million tweets coming into their system per day. Okay, that is a very, very massive number. What that translates into is there are roughly 5,700 tweets coming into the system every second on an average. Okay, at peak loads, this number increases to 12,000 tweets per second. Okay, so now let's try to look at how do we design a system which can scale up to these numbers and maybe even more. First, let's classify all our users into some categories. We'll be having 5 categories in which we'll divide all the users, and then we'll handle each category of users in a slightly different way. Okay, so the very first category is something called as famous users. Now, these are the people which have huge number of followers on Twitter. These could be people like politicians, these could be celebrities, sports persons, or CXOs of some companies, right? We'll come to what different we'll do later on while we are designing the system, but I just want to classify the list of users to start with. Okay, the next set of users are the active users. Now, the definition of active for a platform like Twitter can change over time, but the main idea here is people who are accessing Twitter in last couple of days or couple of hours are classified as active users. In all of our discussion, we'll assume that people who have accessed Twitter in the last 3 days are active users. I believe in the real implementation of Twitter, they consider people who have accessed the system in last 30 days as active, but I'm again not too sure of that. Okay. Now the next category of users is something called live users. Now these are the subset of active users. Okay. And these are the people who are actually accessing the platform right now. Something like the online feature of Facebook or any other platform, right? Now these users will be interacting with them in a slightly different way, so as to improve their experience. Okay. And as soon as a person goes offline, they are moved back to active status. Okay. Now, passive users are the people who are not in any of these categories but are having active accounts. Okay, these are the people who have not accessed Twitter in the last 3 days fundamentally and are not famous. Okay, inactive users are basically the deleted accounts, you can say. We don't delete really any users, we do a soft delete. So that's another kind of users. We don't really do anything for them, to be honest. Now, let's look at an overall architecture of the whole system. Now this whole system is fairly big and there are a lot of components, and it will become too cluttered if I like kind of put that whole thing at once. So what I've done is I have divided it into three components. The very first is the user onboarding flow on how do they come into the system. The next section would be the tweeting flow, which talks about how do they post a tweet and how do they get the various screens that they have access to, like their home screen, their user screen, and all of that. And the next section will talk about search and a bit of analytics that we want to do. Okay. So, on also one thing I want to call out, so whenever you are designing a read-heavy system, so in this case, this has 100x more reads than the number of writes that are happening. So whenever you design such a read-heavy system, you need to kind of make sure that as much as possible, you need to either pre-compute information or cache some of the information. So a lot of things that we'll go over would require a kind of a caching implementation somewhere, so just keep a note of that, and whenever you try to come up with your own designs, just make sure you have enough caching in place to make sure the latencies are well in control. Okay, and a bit of convention to start with before we start. So everything in green is basically a user interaction point. It could be a UI that we give out to users to which they interact, a browser or a mobile app, could be anything. The things in black are basically load balancers, and along with load balancing, they take care of being a reverse proxy and a authentication authorization layer in between, so that they can authenticate all the API calls coming from outside system into our system. The things in blue that you see here are the REST services or the web services or the Kafka consumers that we've written by our own. The things that are in red are either some clusters, some databases, or some open source tools that we have used. Okay. So with that, let's start with the very first user interaction, which is basically their onboarding process when they come in and register themselves on our platform. So there's something called user service, which is basically the source of truth of all the user related information in our system. Okay, and that user service will power the login flow, the register flow, the user profile screen, and a lot of things. Okay, that user service will also power a lot of internal tools and APIs required for serving internal tools. So for example, if some other service wants to get information about a particular user, they might want to query user service. Okay. Now, as far as the APIs are concerned, this has a get APIs, a set of get APIs to get by a particular user ID, to get by email ID, and all of that. It will have some post APIs to update the details of a particular user, and it will also have a very important bulk get API. So whenever somebody wants to fetch the information of a lot of users, so for example, if there's a screen on which you see the followers of a particular user, so there'll be a lot of followers, right? So instead of calling this user service one by one for each user to display their name, their email ID, their photo, and all of that, we could very well make a call with probably 20, 30, 40 user IDs in request and information about all of them coming at once in the response to save upon the network bandwidth, right? So that is user service. Now, user service sits on top of a clustered MySQL database. Now, this user information is a very much relational information. From a scale standpoint, it has millions of users, but they are still finite enough, and it will not go unboundedly. Plus, logically, it is a very relational model, so it makes sense to use a MySQL here. Okay, and we'll be doing certain optimizations on this MySQL. So, this user information is a data which doesn't change too frequently, right? So once a user comes in and gives their information to us, very rarely would it happen that they update some information, right? So this is more of a write heavy system, and a bit of reads do happen on it. But reads are mostly powered by a Redis cache that I've put in place. So what happens is Redis cache is basically a image of a user database, and which has a key of user ID. So whenever somebody hits user service to fetch details of a particular user, it first tries to look up in Redis that do I have information about that user or not. If it has, it returns from then and there. If it does not have information in Redis, then it will query one of the read slaves of this user database, get the information, store it in Redis, and respond back to the client. So when the subsequent requests come from the same user, they can be served out of this Redis cache. Okay, now we have a lot of information that is stored in Redis. Here's a list of all the things. We'll go over them one by one as and when we get to those components. Okay. So user details is one of the things that we talked about. In all of these information, the key is the user ID and value is some object of this type. Okay. Coming to the next interaction, which is the user follow process. So any particular user of this platform can go to someone else's profile and then follow them, right? They might want to get certain information about the following process, like they want to know who do I follow or how many users follow me. All of those things are basically this piece of interaction, which is powered by something called graph service. Okay, the reason it is called graph service is because it creates a network of how everybody in the ecosystem is connected. Okay. Again, Graph Service has a lot of APIs. Basically, first of all, to add a new follow link. It'll also have APIs to get all the followers of a person and get all the people who this person is following, right? It will also have some bulk APIs very similar to user service, which will be get all the followers of a list of users or get a list of users of a list of users who are being followed, right? A bit complicated, but let's go over how that is kind of implemented. At the crux of it, it basically sits on top of another MySQL database. Now, these are two different MySQL clusters on which this data would be residing. This would be a fairly larger data, so we'll have to probably look at sharding that data. But at the very core of it, think of it like a logically one table which has a user ID, a follower ID, and a timestamp on which the transactions happen. There'll be a lot of other attributes, but logically there'll be these two columns, user ID and a follower ID, right? Now again, this is a data which does not get updated very frequently. Overall, at a larger layer across all the 150 million active users per day, this would be updated, but for one user, it wouldn't get updated too frequently because if you look at yourself, how frequently do you go and follow somebody? It doesn't happen every minute or every hour, right? So that is the reason it makes sense to cache this information as well. Now, there are two kinds of information that we need to cache. First of all, given a user ID, what are the list of users that this person follows, which is basically this following thing. And then given this user ID, who are the list of users that follow this particular user, which is basically the followers of this user, right? So these are another set of two information that we are storing in another Redis. Or in fact, we could use the same Redis here, okay, because it's anywhere clustered Redis. Again, similar to user service, all the APIs that come to graph service first try to get from Redis. If they don't find information, they query the MySQL. Then they persist into Redis and respond back to the user. Okay. So these were the user flows. There's another thing which we need to talk about. So whenever a user is interacting with Twitter, right, there are they are sending certain signals even if they are not explicit. So let's say if they are browsing through a list of tweets that they go through, and let's say if they spend a lot of time on one of the tweets, they are kind of telling that they have interest in this tweet, right? There could be a lot of other information that we can gather out based on the way people access the whole platform, right? So whenever we find some event of importance that is happening on the UI, this UI could be a browser, could be an app, anything, right? We do send an event saying something happened. Just track it and then we can use it for analytics. So all of such events would be sent through this load balancer to a service called analytics service, which will be putting it into a Kafka. Okay. What happens with that, we'll probably look at in subsequent sections. Okay. Coming to the last service in this. So remember the user grouping that we created of famous users, active users, live users, passive users, and all of that. There was something called live users. These are the users who are using our platform right now. Okay. So let's say if I'm using Twitter right now and one of the people who I follow posted something, it would make sense to just so that I don't have to open the app, refresh or do something if it just somehow comes to my phone, right? Or let's say somebody has tagged me in a tweet and if I get notified about that, that will be a nice user experience. So what that is done through this service. Okay, what this service does is it basically keeps a connection open with all the live users. Okay, and whenever any event happens that needs to be sent to this user, it happens via that WebSocket, right? Now, how does this come into play? We'll look at in the other sections in more detail, but for now, this information is good enough. Okay. Now, along with this, there is some other information that we are capturing as part of the interactions between the user and the server, right? We are basically capturing till how much time the user is actually live. Okay. And when this communication between the two parties stop, we do realize that the person has gone away, closed the app, closed the browser. The person is not live anymore, right? All of that information is also of importance to us because now if the person is not live, we cannot send them this kind of a notification. We need to do something different, right? So that information also needs to be stored somewhere. So that information will be put into Kafka saying the user is not live anymore. He was last live at a particular timestamp. That information would go through all the way to user service. It will store it in the cache saying the user type has now moved from a live user to an active user. His last access time was some particular timestamp. Okay. And then other systems can use that information to modify the behavior in certain cases. Okay. Now let's try to look at what happens when somebody posts a tweet, which means adding a new tweet. Okay, so first of all, tweets could contain text, it could contain images, it could contain videos also possibly. Okay, so let's just say if it's an image or a video content, we'll have something called an asset service. What that does is it is responsible for all the multimedia content, which could be videos, images, anything of that sort. It takes care of uploading it to wherever it needs to, and even when somebody needs to see it, this is responsible for displaying the content. Okay, if you want to get into details of how asset services built, I would recommend so I've already made a video on the design of Netflix and Amazon Prime, basically a video hosting platform. So asset service is basically our video hosting platform here. Okay, so I would recommend to watch that video instead of going over the nitty-gritties here. Okay, but assuming we have a platform which takes care of all the images and videos and all of that, now we are just left with a tweet which can have a text and a couple of links. Okay. Now a link, whenever we talk about a link, even if somebody wants to paste a link in the text of a tweet has a constraint of 140 characters. So you anyway cannot paste a big text there, right? So first of all, what you need is a URL shortener. Okay. So whenever you want to post a big URL, there'll be a URL shortener which will give you a short URL instead of the big URL, and you could post that. Okay, assume that can be taken care of in UI automatically, and for the backend of it, we'll have a short URL service. So I do have another video on the design of tiny URL. Just think of it as a tiny URL system. Okay, and details of this short URL service can be looked up on that video. Now, assuming we have these two components, All we now have to handle is basically storing a text of a tweet and retrieving it when we need to, right? So all of that functionality goes within the tweet ingestion service. Okay, so each time a person posts a tweet, basically types a text, hits a submit button, that basically makes a call to this tweet ingestion service. Okay, which first of all, the very first thing it does is stores it in a permanent data store. We are using a Cassandra for storing the tweets. Now, why Cassandra? Because we have a massive amount of data. Okay, first of all, we have millions of tweets per day, and and Cassandra can easily handle that scale. Now, other than Cassandra, we could have possibly used HBase also here. Both Cassandra and HBase are equally competent enough to handle the data of this scale and for the use case and the kind of queries we have. Both have a bit of pros and cons. I chose to use Cassandra because the setup of Cassandra is fairly easy. If you want to set up HBase, we'll require a Zookeeper or a Hadoop cluster, and that adds a lot of maintenance. Okay. Now, assuming Cassandra is our data store, think of it very logically speaking, think of it as having a table which has a tweets table, which has a tweet ID, a user ID who posted the tweet, and a tweet content, and a couple of other attributes. Okay, so this is how the structure would look like. Now, ingestion service is just responsible for posting a tweet. Okay, it doesn't provide get APIs and all of that. Once it is posted to Cassandra, what it does is it puts an event into a Kafka saying, I've got a new tweet whose tweet ID is so and so, whatever that tweet ID is, which is auto generated by this service. It has been posted by this user ID, and this is the content. Whoever needs to do whatever, go do your job, right? So this tweet ingestion service puts this message into this Kafka, and the flow of tweet ingestion is over. So this is how we have saved a tweet. Okay. Now let's get to other side of things. But first we'll go over a couple of components that we have built to a couple of platform components. So there is this tweet service that I have. This is basically a source of truth service for all the tweets. So this basically sits on top of this Cassandra cluster and owns the schema and the data within that. Okay. This tweet service will provide you all set of APIs that you need to display any tweet. So get by tweet ID, get tweets of a user, all those kind of APIs are provided by this tweet service. And whenever somebody's timeline need to be generated, that is also powered by this tweet service. Okay. Now, for a second, quickly jumping on the user side of things, and then we'll get back to how the flow works. So when somebody wants to look at the tweets, okay, on the read flow, there are two kind of views that a person can have. Okay, one is called a user timeline, which is basically a timeline is basically a series of tweets ordered by something, generally by timestamps. Okay. Now, user timeline is basically your own timeline. This basically contains all the tweets, all the retweets that you have posted. Okay. Then there's something called home timeline. Home timeline is what you see on your home page. So all the people that you are following, all their tweets will show up in your home timeline. Okay. So generally, very logically speaking, construction of user timeline is basically select star on Cassandra, where user ID is your user ID, and construction of home timeline is logically select star from Cassandra, where user ID in all the people you follow, right? Now these list of people that you follow could or possibly be thousands of people, right? So, and making this query at runtime would end up, it will be something like, first of all, fetch a user's followers, like all the people that a user follows. And once you have that list of people, get all their tweets and then arrange that. If that would be a very okay enough naive implementation, but that would not scale you know, at a scale where we have 150 million users accessing our website daily, and that too hitting this API call multiple times in a day, right? We'll have to have that will first of all slow down things a lot if we start querying Cassandra for each thing, and it'll just not be scalable enough. Instead, what we are trying to do here is we'll cache the user's timeline. We'll say that we know there are some active users who will come to our website. Instead of calculating at runtime, we'll pre-calculate all of their timelines and just show it to them then and there. Remember the non-functional requirements that we have. Whenever a person comes on their home screen, they should be able to see their timeline very, very quickly. Okay, so that's the approach we are trying to follow. So remember now, whenever people are tweeting something which is going to a Kafka, now there is a tweet processor. What that tweet processor does is it basically sees that, okay, user one has tweeted something. Now let me try to get their followers. Okay. And let's say it figures out that there are some users whose timeline needs to be updated because this tweet will now show up in all of those users' timelines, right? Then it will create the timeline for all of those users and put it in this cache. So now when those users try to come on their home screen, they just do a cache lookup and their view is sorted, right? So if I just have to list down the things, it basically is something like, let's say user one posted a tweet T1, okay? And user one is followed by, let's say, U2, user 2, user 3, and user 4. So what this does is it basically in the timeline of user 2, user 3, user 4, it puts tweet T1 along with what all other tweets it had, right? So each of their timelines could have a lot of tweets. This now it is appended and at the very beginning. Similarly, there are a lot of users posting tweets, right? So all the tweets are coming here. This service is identifying all the followers and whole of that mapping and then updating all of the people's timelines. Okay. So this is basically how we are trying to do. Now this service needs to get basically a list of all the people who are being followed, right? So for that it will query the graph service. I have not made the link, but tweet processor will query the graph service to figure out all the users. Basically this U1 to this U234 mapping, this will be queried from graph service. Okay, all good till now. But there are a lot of problems in this design. The problems are because we are maintaining everything in Redis. Redis first of all is a in-memory solution. So it will put all the data in memory. What that means is we need to have massive amounts of RAM. Okay. Now, if we try to keep timelines of all the users in memory, that's something very inefficient. Okay. That's the reason I kind of categorize the users in the very beginning. Okay. So only those users' timelines would be stored in Redis who are active. Okay. If a user is passive, we kind of know that the user will not come on Twitter for a while. So why bother to create the timeline, right? We'll create the timeline when the user logs in. Cool. Okay. Uh, Now that is one side of the problem. So if we kind of just list down what happens for each user, for all the active users, all the data is in Redis. Now what happens if a passive user comes in, right? How does that passive user see their timeline? So in that scenario, all the requests for this timeline will come to timeline service. Okay. The flow is that these are the UIs through which the users will request. Those requests will come to timeline service. Timeline service queries Redis for all the active users. Okay. It is easily able to figure out who are the active users by querying user service, which anyway has a user to type mapping in its own cache. Remember the previous section. Okay. Now once timeline service figures out that the user is a passive user and I do not have its data in Redis, what it will do is it will essentially query whoever it needs to in the system, try to figure out all the data that it needs to figure out, and then it creates the timeline. So what it does is essentially, it first of all queries graph service saying that I've got this new user whose timeline I need to create. Give me all the users who this user follows. Okay, so it gets a list of users whose tweets would now be shown. Then it queries the tweet service to give all the tweets of all of these users. Obviously, it will not be all the tweets, it will be some tweets till sometime in the future, and then it can be a paginated kind of a thing, right? Once it gets all the tweets of all those users, it now arranges them as per timeline, as per the timestamps, stores it back in the Redis, and returns to the UI. Okay, so now we have a solution to handle active users, passive users. Okay. Now, once active and passive users are handled, we could do some kind of optimization for the live users. Remember, live users are the users who are online right now. Okay. Now, those users are anyway sitting on the Twitter app. They don't need to really follow all of this process. what we could do is the tweet processor anyway knows that who all's timelines have to be updated, right? Anyway, and all the tweets are anyway coming to this Kafka, and we also know that who are the live users. Okay, once we figure out that, once the tweet processor figures out that a particular user's timeline is to be updated, and if it figures out it's a live user, it actually puts back an event into Kafka. And then comes the live WebSocket thing that we talked about in the previous section. At that point in time, it was just used to check if a user is live, but this thing can actually send a notification to the app, right? Now, again, reiterating over the flow, an event comes to Kafka, tweet processor tries to update Redis. But while updating Redis, it will also get to know that this user is a live user. So it will put back an event into Kafka saying whoever is responsible for sending this notification down to the user, go send it right away. Don't wait for the person to query back, right? Through this route, it will come to the user app, and the UX should be able to handle it, saying you have more tweets and just scroll up or scroll down and something of that sort. So now even live users, they don't need to ever even query Redis. While they are on the app, they will keep getting those notifications, and newer tweets will just keep showing on their UI. Okay, cool. But this still has a lot of problems. So as of now, if I look at Donald Trump, he has roughly 75 million followers. Okay. What that means is each time Donald Trump makes a tweet, there needs to be 75 million updates, okay, for each of his tweets. Now that's a lot of that's a very big number. Okay, and that's fairly inefficient if we start updating 75 million records on the update of one person, right? And if he starts tweeting very, very frequently, then we are in for big trouble. Okay, so instead, what we could do is remember now we have something called famous users. Those are the people who have big number of subscribers or big number of followers, right? We will not do any of this thing for the for those kind of users. What essentially would happen is timeline service will take care of merging everything. So timeline service knows that Redis has data only of tweets of normal users. Okay. So once it gets the data of all the users, it now tries to figure out that what are the tweets that should be shown to this user of famous users. Okay. So timeline service then basically queries graph service again and tries to figure out who are the famous users that this person was following and get their tweets as well. Cool. Now, timeline service, after querying from graph service through tweet service, has all the tweets of a person like Donald Trump. Timeline service also has the tweets of normal users, and it can show it to the UI, right? But before showing it to the UI, it can then update in Redis. It can update in Redis saying that I have not just captured the regular users, I have also captured the famous users. Cool. And not it'll also add a flag saying that I have updated the data in this particular user's timeline of famous users at a particular timestamp. Okay. So now what data structure it stores is something like a list of tweets plus a timestamp TI. Okay. Now the next time we get a request from the same user, we basically see this timeline service looks at this timestamp. If this timestamp was probably 5-10 minutes before, then it can again query the tweets of some famous users from tweet service because those could have again tweeted in the last 5-10 minutes, right? But if this timestamp is just 5 seconds in the past, we can safely assume that there is no new tweet and just return from this Redis directly without querying the tweet service and then the Cassandra and all of that. Okay, so famous users will kind of handle in a slightly different way, just because if we try to handle it in the normal way, it is going to put up a lot of load on various components in the picture. Now the only thing left is inactive users. So those are user accounts that are anyway deactivated. So those users don't really log in. They can't even log in because those are deactivated accounts. So we don't need to do any of these things for those kind of users. Okay. But now coming to the famous users. Now, there could be certain users who are famous who follow some other famous users, right? So, let's say Donald Trump is following Elon Musk, for example, right? And both have millions of followers. So, what we could do is neither of the tweets will follow, so both of their tweets will not go the Redis route normally. But if Elon Musk tweets, then Donald Trump should get notified at least. At least the famous users within themselves should get to know of each user, right? So those kind of things could be handled by tweet processor. That whenever a tweet of a famous user comes in, don't update the cache of all the users, but just update the cache of other famous users that are following this user, right? So those are some nitty-gritties that can be handled depending upon the depending upon how is it that you are trying to build the system, right? But in general, this is something that should work out fairly fine. Okay. Now, what could potentially be the bottlenecks here? This Cassandra could be a bottleneck. Why? Because there are a lot of times when you are querying this. Okay. This Redis is definitely a piece that needs to scale up. Why? Because this is something totally in RAM. So we need to take care of these couple of components and then Kafka, of course. So these three components are something that we need to really look at and optimize as much as we can. And also make sure that we have enough. So at least on Redis and all, we should have enough TTL so that we don't keep really old junk data. So cleanup and all should be taken care of on these components. Other than that, everything that you see here is even these components that you see here, Redis, Cassandra, Kafka, everything is horizontally scalable. So as and when the number of tweets in the system increases, all we need to do is add more machines into each of these components, and then things should kind of work just fine. Now coming to the last part, which is search and analytics. Let's first look at how does search work. So by search, what we mean is if somebody wants to search for a particular text, we want to show them all the tweets that have that particular string in that, ordered by some relevance score. Okay, so let's look at how could that be built. So remember the tweet ingestion service that we talked about in the previous section, which was basically the entry point of all the tweets into our system. And it used to put an event into Kafka, which was read by a service for putting into Redis, right? Now there could be a lot of other consumers who are consuming the same data. Okay, one of such consumers is a search consumer. What that does is it basically looks at all the tweets, basically consumes all the tweets that are coming into the system and stores it in a database, okay, which will then be used for searching. And it uses a database called Elasticsearch, which is a clustered NoSQL database, very efficient for text-based searching. Now, why Elasticsearch? So the requirement here is we need to do a text identification, first of all, and a relevance, right? So we need to first of all identify all the tweets which have a particular search string that the user has mentioned, and out of all the tweets which have that particular substring, now rank them in order of relevance. Now there are various implementations to it. A very basic implementation is something called TF-IDF, which is term frequency inverse document frequency, which basically tries to look at how many times a particular word has come in a document and against all other words, and then tries to rank it accordingly. Okay. Now Elasticsearch uses Lucene to power all of those kind of things. So any Lucene-based database could work just fine. Okay. Now once search consumers processes all the data and stores it into Elasticsearch, it is basically ready for search. Okay. Now coming to the user side of things. A user can then basically give a search string as an input, which would come through the search UI. It would talk to a load balancer and talk to the search service. Okay, the search service would then query Elasticsearch, get the results, and give it back to the user. Okay, so this is how we complete the loop. And search service and search consumer are very well aware of the contract. So consumer is basically writing and search service is reading from the data store. Good. Now, if we go over the non-functional requirements that we talked of something that there is some lag okay in some of the use cases, right? So let's say if I posted a tweet and let's say if you are searching for something, if you do not get my tweet, it doesn't really matter too much, right? Or maybe if you get that tweet 5 minutes later, that is also fine. So what we can okay, and that is the functional side of things. And the way search works is, let's say some event happens in the world, people start searching for it. A lot of people start searching for it together, right? And then slowly after a while, that whole thing dies out, and then nobody keeps searching for that word, right? So with this assumption, what we can say is, if something is searched for, it is possible that somebody else would also search for the same thing, right? Now we don't need to compute the search results again and again, because the moment we start querying Elasticsearch again, it would have some kind of caching, but it will not. It will still try to actually make a full search and return the latest set of data also. Now we can live without latest set of data. So what we'll do is, once the search service gets a set of results from Elasticsearch, it'll put it in the Redis. Okay, and it'll put it in the Redis with a time to live of let's say 2-3 minutes. Okay, so what we are saying is, till 2-3 minutes we'll have that search result. After that it'll expire. And now, instead of querying Elasticsearch, search service, when it gets a request, it'll first query Redis. If it gets a result, well and good, it will return then and there. If it does not get a result, it will then query Elasticsearch, get the search result, store it in Redis, and then respond back. So this way, by adding Redis, we will effectively reduce a lot of load on Elasticsearch, and which includes the computation cost, and which kind of translates into money, because the more the number of queries you have to do, the more hardware it will be required, and effectively Redis would be a much cheaper option there. Cool. So this is about search. Now let's look at some of the analytics that can be done on top of this data. Again, going back to the same Kafka, wherein a series of tweets was coming. One very common feature of Twitter that you see is something called what is trending right now. And it's not just Twitter, anything in any such kind of platform, you would want to know what people are talking about, right? What we could easily do is, on top of this Kafka, have a very simple Spark streaming consumer running, which basically just checks for what were the most common keywords in last 1 hour. Right now, it need not be just the hashtags. What it could do is, let's say there is a tweet with a lot of words. It basically tokenizes the tweet, basically splits each string of tweet by a space character, and it will get a list of words. And then it will dump all of that list of words somewhere, and then aggregate over last 1 hour to try to come up with the words that were used the maximum. Okay. Now, very likely these will be very common words like a and the, is, of. So it can remove some of these top words and then come up with a relevant set of words which are actually something that people are talking about, right? That can be basically used to power the trending kind of a feature. So even though we didn't talk about it as part of functional requirements, but this will be a good thing as an analytics. So what we could do is have a trend service which Spark Streaming will write to every, let's say, half an hour. Okay, it looks at last 1 hour of data and dumps in what all are the trending things right now. Okay, and there could be a trends UI which can be built on top of this service, and it kind of powers that UI. As a storage, we don't need this to be a we don't need a database for it, because this is anyway temporary information. We could again use a Redis for storing it. Okay, as a cache, because it will anyway, again, in the next half an hour, Spark Streaming will again give a list of trending words to this service again. Okay, now we've used a lot of Redis here. So even though it's an in-memory data store kind of a thing, but it does have the option to store it to disk. So if, let's say, there's an outage and there's a downtime and the cluster, some of the machines in the cluster go down, you still have data persisted on RAM, on the disk, sorry. So it's not very, it is a bit fault tolerant as well. Good. Coming to the next set of things. This, and by the way, this trends could, right now we just talked about trends in general. These trends could also be calculated at a geographical level, saying what are people from India talking about, or what are, or people from, let's say, France talking about, or any such thing. Okay, now let's say all the tweets that we have, we might as well put it into a Hadoop cluster, because in a company of Twitter scale, there will be a lot of analytics done, right? Something similar to trends is one of the options. There could be other lot of analytics, right? Something like who is right now the most engaging tweeter, or who is the person on whose tweets have been retweeted the most, or stuff like that. All of those could be answered by various kinds of queries, which can be powered by Hadoop. Okay, not just by Hadoop, but tools on top of that. Okay. Now, a very common use case could be something like the newsletter that a lot of these companies send. Twitter also sends that. There are a lot of companies which sends weekly newsletter about various things. It could be things around business. It could be things about some new promotions that they are launching. Right. So all of those promotional content could be powered by it. Let's look at an example. So let's just say we have a weekly cron job, which basically is responsible to pull back all the passive users. So passive users are the ones who are not using the platform frequently, and it is good for Twitter if they start using it, right? So to engage those users, Twitter could start a weekly email which talks about some of the very, popular tweets in the last 1 week, right? Now those popular tweets, if it's just one list, it would not make it would not be personalized and it will not make sense to a lot of people. So what could be done is a nice ML kind of a thing there, saying for which passive user, what are the most relevant tweets in the last 7 days that this person would be interested in. Get the list of, let's say, top 5 tweets and send them a notification, right? Saying these are the tweets that you have missed. Why don't you come on the platform? So this could be used as a re-engagement kind of a platform. There could be a lot of other things that could be done on this, right? Now, how would that notification be sent? There would be a notification service that will be invoked saying this is the user, these are the tweets, go send the content. The notification service can talk to the user service to get the email ID, phone number, and stuff like that. It can then find the user's communication preference from its own data store and then send out a notification, whether it's an email or SMS or maybe an in-app notification, whatever that is. So I've done another video specifically on how to build a very scalable notification service. So if you want to get into details of that, you might as well have a look at that video. But overall, this is something that would work out just fine for a Twitter kind of a system. Now, at Twitter scale, all of these things are good. But let's just say that, the scale increases 5 times. Or let's just say instead of Twitter, it is Facebook. Now, how do you design that? So there are a lot of things that will need to get changed. Why? Because a lot of things here, we are doing it in memory. If the scale increases 5 times, then it becomes a lot difficult to do all of that in memory. So all of those things I'll be covering in another video in which we'll be talking about how to design Facebook. So yeah, I think for Twitter, I think this should be it. Thanks for watching this video. If you have any suggestions on what videos we should make next or how we could improve this one, do let us know by commenting here. And don't forget to subscribe to this channel, like the videos, and share the videos with your friends while we keep working to get more such content to you. Happy learning!